Hello, everyone. My name is Martin from Seoul National University, and I'm here to present our work titled MetaSafe Compiling for Protecting Smart Pointer Metadata to Ensure Safe Rust Integrity. Our work majorly focuses on smart pointers in Rust and how they contribute to its memory safety. We look at situations where attacks on smart pointers and their metadata can be leveraged to break Rust memory safety. This is conjoined research between Seoul National University and UNIST in South Korea. So Rust is a growing system programming language that has gained popularity thanks to its memory safety guarantees and promises. And currently, it's being adopted by major companies in production, including Google, Amazon, Microsoft, and so many others. It's also being adopted in major open source projects, such as the Linux kernel and the Android operating system. And there are already testimonies of reduction in memory bugs thanks to its adoption. What's interesting about Rust is that as it maintains memory safety, it also maintains performance. And in some cases, it's been reported to be faster than C and C++. And therefore, some companies are actually replacing some of their C++ code with Rust. The Rust memory safety is built on an access policy, which depends on three major rules. The first one being ownership, and dictates that a memory object shall have a single owner at a given point in time during execution. The second rule is borrowing, which is like a concept, whereby although we have one single owner, a memory object may be borrowed either immutably by multiple entities or mutably by one single entity. Finally, we have lifetimes, and the rule here is that a memory object cannot be accessed unless it is live. For example, if you free an object, you cannot access it anymore. This policy is majorly enforced by the compiler using a borrow checker for borrowing and ownership and a lifetime analyzer for lifetimes. The problem with these rules is that they are too strict for modern day software development, and at worst, for example, we can't even adhere to them while programming widely used data structures. An example we take here is a doubly linked list, which we might all know. In this case, we know that a single node will have at least a pointer from its previous neighbor and another pointer from the next neighbor. In the case of Rust, this is double ownership, which will break rule number one, and that means we cannot actually design a doubly linked list while adhering to the ownership rule. So Rust presents a workaround this in two ways. One is using unsafe Rust, whereby you can use raw pointers, but of course, as the name says, that's unsafe. The other way is to use smart pointers. Now, I'm not saying that smart pointers and unsafe Rust are mutually exclusive. They can be mixed together, of course. But in this talk, we'll focus on smart pointers. There are many smart pointers in Rust. Some of them have metadata. Some of them simply have APIs, and they are diverse depending on their roles. For example, we have the vec smart pointer, which has a pointer to a buffer, some length metadata and capacity metadata. We have shared reference counter pointers, such as RC and ARC, which would be the solution to our doubly linked list problem. And we have smart pointers for interior mutability, which will have special metadata. These present a face that they are immutable to the compiler, while their data that they hold can be mutated using APIs that they have. The question we have here is the storage of smart pointers and their metadata. We found that actually, even though smart pointers and their metadata perform such a big role in Rust memory safety, their metadata is stored alongside other data in a program. In this example, we show that a vec smart pointer is stored near an array, and any buffer overflow on an array can be used by an attacker to change the metadata of the vec. For example, we can change the capacity or the length. And since the vec smart pointer depends on this metadata to perform runtime checks to ensure memory safety, by changing it illegally, we can actually break Rust memory safety depending on vec. Smart pointers also have APIs. Some of them are public, some of them are private, but it also has unsafe APIs, which allow a programmer to change the metadata at will without any checks. In this example, we have a string, a pointer to a string that is sent to a test function. And inside the test function, we see the pointer actually being dropped and returned to the allocator. When the function returns at line 15, the user can actually recreate the box smart pointer from an already freed pointer. And on line 16, that pointer is dereferenced, causing a use after free problem. The next example is actually prevalent in Rust programs on the vec and buffer related smart pointers. In this case, we see that the vec presents a public, unsafe API function called setLength, which allows programmers to set the length at will. And in this case, we can see, it's a simple example, but we can see that Rust allows us to set the length to 10, even though we can actually see that the buffer length is 3. And at line 6, we can actually index now with an index 9, even though we know that that's already out of bounds. There are several works existing about enhancing Rust safety, and most of them focus on isolating unsafe Rust from safe Rust. It's important to note that our work does not intend to replace existing unsafe Rust isolation works, and rather we intend to complement them to further enhance our Rust memory safety. So briefly, our work intends to protect smart pointers and their metadata, and also validate any metadata updates that might be performed at runtime by the user. And this has some requirements. First of all, identifying smart pointers. Now, although I've presented them as something special, they are not actually seen as anything special by the Rust compiler, and they're just seen as normal data structures. Of course, they implement some special traits like drop and deref, but some of them don't. Therefore, we need a way to recognize a smart pointer. Next, we need separate isolated storage for storing them aside from other user data. We also need control, a write access, the metadata. And finally, we need a way of authenticating metadata updates and its ground truth. An overview of our work is like this. So first, we divide the code into regular code and smart pointer and allocator domain. Then we divide the data into regular data and smart pointer metadata and allocator metadata. Then for access, we allow regular code to read and write regular data, but we only allow it to read smart pointer metadata and allocator metadata. We deter any writes by regular code to smart pointer metadata or allocator metadata. Finally, the allocator domain and smart pointer domain are allowed to read and write smart pointer metadata and allocator metadata. To identify smart pointers, we require users to implement a special trait, which we call meta update. So if a user thinks that their data structure is possibly a smart pointer, for example, it implements deref or drop, they can implement this trait. And inside this trait, they are required to define a function which we can use to check the validity of the state of the smart pointer. Then whenever an unsafe API function is used to change the metadata, we follow that with a check for the validity of the smart pointer, and if the check fails, we panic the program or the thread. For isolated storage, we rely on the stacks. For example, we use safe stack, the same idea, whereby we have one stack for smart pointers and their metadata, and another stack for regular data. And then for the heap, we require that an allocator should have a grouping property, such as arenas in tcmalloc or heaps in memalloc. For our prototype, we use memalloc and its heaps. So we use heaps 0 for FFI, we use heap 1 for smart pointers and their metadata, and heap 2 and onwards for regular data. For access control, we rely on Intel MPK because it allows us to perform checks while maintaining performance. And whenever we are entering in a smart pointer domain, we enable write access to the smart pointer data. And when we return, we revoke access using a few instructions. Another challenge we find while implementing our prototype is struct inline smart pointers. As the example shows here, the struct farm has a smart pointer vec of employees as a field, and the other fields are not smart pointers. The challenge here is a decision on how to treat such a structure. For example, should we treat this as a smart pointer as a whole, or should we treat it as regular data? So what we do here, we just go on to create shadow memory in the gated region of the smart pointers, and any accesses to the employees field is redirected to the shadow memory. We evaluate our prototype to measure the performance and memory overhead, and we find that for micro benchmarks, the performance overhead is 25%, while for real-world programs such as Servo, which is a browser written in Rust, we find that our prototype incurs only 3.5% performance overhead. In terms of memory, we measure the memory overhead using the micro benchmarks, and we find that for single-threaded micro benchmarks, we incur a 27% memory usage overhead. But for heavily multi-threaded micro benchmarks, we incur 8 times more memory usage. And we found that this is due to each thread needing a separate stack for the smart pointers, even though it might not use it. So when we turn off that, we find that the memory overhead drops to 31%. As I said in the beginning, we don't intend to replace existing unsafe Rust works, so we try to combine MetaSafe with another work that isolates unsafe Rust from safe Rust, which is T-Rust. And then when we combine them, we measure the overhead in this case, and we find that T-Rust plus MetaSafe incurs a performance overhead of 13%, while T-Rust alone incurs an 11% performance overhead. In terms of memory usage, we find that MetaSafe and T-Rust combined incur an 89% memory overhead, while T-Rust alone incurs 69% memory overhead. And this is due to the need for separate memory for smart pointers and their metadata. In conclusion, we present MetaSafe, a mechanism to recognize and protect smart pointer metadata and enhance Rust memory safety. We allow programmers who might have custom smart pointers we give them a way to mark their smart pointers and provide means for validating them. And we rely on Intel MPK and compiler instrumentation to maintain a reasonable runtime overhead. Our work is already open sourced, both at GitHub and Docker, so it's open for access. This is the end of my presentation. Thank you very much.